Okay, we're going to try to do this set in one take. Let's see if this will work. Do. Okay, so very first problem is n being a real number and epsilon being some positive real number. So epsilon is some positive real number, and we're given that n is also some number. So we're being asked if there exists a big N that's kind of like a threshold, such that if little n is greater than or equal to big N, then 1 over n plus 1. I don't really know why there's absolute values here, but they're asking if that's going to be less than epsilon. Well, just to see this a little bit, right, you can kind of rearrange this. And this is basically saying whether or not 1 over epsilon can be less than n plus 1 for every little n greater than big N. So what this is sort of essentially suggesting that we do is basically saying, well, okay, you have some like tiny value 1 over epsilon, right? Well, 1 divided by a tiny value is going to give you some pretty large value. But the idea here is that hopefully you can always choose like a big N, right? A big N that's larger than 1 over epsilon, such that, well, excuse me, uh, such that, well, you know that little n is greater than or equal to big N, so you have a relationship like this, right? So let's see, what else is there to say? The plus 1 seems to be just like a little bit of hedging to make sure there is no like off by 1 errors. But the idea basically here is it all comes down to whether or not this is true, right? For any positive, no matter how small epsilon, is it the case that 1 over epsilon is less than capital N? And this is a topic of some discussion, right? It's something called Archimedes' principle. You can go look that up. I don't know if you necessarily need to cite this for your particular homework, but when I learned this principle, I learned this as Archimedes. Uh, well, I mean, this is the name I learned it as. And like philosophically, it really does just seem like it never bothered me. The point is, for some people, it bothers them just the idea that you can always choose an n large enough for this to be true. Like this never bothered me. This like I've never really understood the issue with it, but for some very careful mathematicians or philosophers, they kind of uh, try to make clear that this is an axiom, like an assumption that this can be done. Anyways, go look that up and maybe talk about it in some detail if the class has introduced that kind of principle before. But anyways, let's keep moving onwards. Yeah, very similar. So now epsilon is equal to 1/6, and we're interested in, okay, so for all little n greater than or equal to threshold, capital N, greater than 0, we are interested in whether to find the smallest choice of big N, such that 1 over n times n plus 1 is, is it greater than or equal to epsilon? Excuse me, it's less than epsilon. Well, okay. Just go ahead and plug in 1/6 here, and you're going to rearrange that, and you're going to find the left-hand side turns into something nice, and then just move the n times n plus 1 over to the other side, and just try to think about the smallest n values that this would hold true for, right? Um, so the notation's a little bit funny, but it's always done this way where little n is sort of acts as the variable, but big N kind of acts as the threshold, the sort of like cutoff for little n. So go ahead, uh, play through with this and see the smallest value of like little n that would make this true. And the smallest value of little n that would make this true is also the smallest value of big N. Try to think that through for yourself. Okay, we're just going to keep up rolling here. What's going on with my computer? Is it freezing? All right. So now we have a convergence sequence, right? So AN converges. n is equal to 0 to infinity with limit L, and all the numbers are positive. So what this goes to L, and every single an is greater than or equal to 0. So the idea is, well, can L be negative? And intuitively, no, right? Because like if every single one of the things that approach it arbitrarily closely is non-negative, then it'd be really, really funny if L could somehow be non-negative. Sorry, it'd be really, really funny if L somehow managed to be negative. And maybe the way to prove this, I think the easiest way to prove this is by contradiction, right? Maybe contradiction, for those unfamiliar with it, the idea is that you start by assuming the opposite of what you want to prove. So assume L is negative, so L is less than 0. And the idea is starting with this assumption and using only perfectly rigorous logic from there, if you can get to an absurd conclusion or something violating something else you know to be true, then that means your initial conclusion must have been false. That's what they mean by proof by contradiction. Right? So if you do all that and prove your initial assumption is false, then of course that means L has got to be greater than or equal to 0. So you're sort of proving the opposite. Sorry, you're proving something by starting off by assuming the opposite. So, okay, let's just pictorially draw out what's happening here, right? So this is sort of like saying there's some sequence that's, gets arbitrarily close to 0, right? But the idea is, okay, so if this is 0 and this is L, what this is saying is that, well, what's the definition of a limit for a sequence? It's basically saying that, like, what is it? Like for every epsilon, um, let's say that epsilon is equal to the absolute value of L for this particular case, right? So epsilon sort of goes up in interval in each direction. Epsilon and epsilon. Yeah. Right. So the idea here is that, what is it? Like for every epsilon, there exists a capital N such that for every little n greater than or equal to big N, uh, an minus L is less than epsilon. So this is the this is the mathematician speak, but in plain English, this is sort of like saying for every epsilon interval, right? That's this like vertical interval right here. It's saying that there's got to be some threshold point. Um, it's saying that there's got to be some threshold point. Let's call that capital N, such that every single point past the threshold point has got to be uh, within this interval, right? It's saying that every single one of these points past this big N has got to be within this vertical interval right here. But this is a little bit broken, right? This is a little bit broken because if it's within this vertical interval right here, well, that means that the points are negative, right? Because this is 0 and this is L, which is negative, and everything inside the epsilon interval, uh, which is an open interval, which means it doesn't include the endpoint of 0, right? Um, by the definition of a limit, it means that all of the ANs are past the big N are negative, and clearly there's some issues here. So try to conclude the rest of that on your own. But this is one of those things where it's just like a single application of the definition, and you're pretty much done. You just have to really be able to parse the definition and understand what's happening. Yeah, we keep going. So now we have this kind of complicated looking limit as n approaches infinity of 1 over, what is this, like n squared plus 1? And what is this? Plus n squared to the m. Right? So what does this actually has to do? We're showing that needs to equal 0. So you can go ahead and state the definition of limit of a sequence here on your own. I mean, it's basically exactly what I had over here, right? But it doesn't hurt to refresh the definition over and over again until you really understand what's going on. But you're being asked to prove that this limit is 0. Okay, so how do we do that? So the thing that's making this kind of unwieldy is basically this +1 in here, right? Because this term by itself we could probably handle all right on our own. Remind me that I think m is a positive integer, right? M is a positive integer? Yeah. So what's making this problem complicated is that we really wish that we could just be left alone with this thing. Yeah? Or in fact, maybe if this question looked like just square root of n squared, the m, and squared m, right, without the +1, this wouldn't be so bad because this is basically just 1 over 2 n squared to the m, right? And we know that, well, the constant factor of a half in front doesn't really matter. So this is basically just, um, what is this? Like the n to the 1 over n to the 2 over m power. And because n goes to infinity, right, because n goes to infinity, this is basically just 1 over infinity. So this goes to 0. This goes to 0. So if we were to just plot that out, that would look like, so I'm plotting out these points right now. That would just look something that goes sort of downwards like that, yeah? But the idea behind this problem is a good application of the squeeze theorem. And what the squeeze theorem is saying is that if this is your original sequence, let's call this like an, and then you have another sequence below it that every single value is less than or equal to, but still not negative, right? So this is the an is the top points, the bn is the bottom points. It's sort of like the an points are kind of squeezing down the bn points. That's the idea, right? It's sort of like, eh, it's sort of like if you can imagine like two people, right? Um, at each like snapshot in time, the an person is sort of like moving closer to bn, and bn is kind of like socially awkward and trying to move away from an, right? And as an sort of moves downwards and downwards and downwards towards the zero, the horizontal axis, bn of course has to move even closer, right? So if an gets arbitrarily close and approaches 0, so does bn. That's the idea, right? That's the idea behind squeeze theorem. And it makes intuitive sense, right? As long as you have a guarantee that both an and bn are not negative, right? Every single one of these values is greater than or equal to 0, which is true for both this and for this. It's always non-negative. Well, this squeeze would apply. So now it's time to actually figure out the relationship between this thing and this thing, right? And the only difference is this little +1 right here, which means that the denominator is a little bit larger. So if the denominator is a little bit larger, what can you say about the relative value between these two? Like compared to the squeeze theorem example, which one of these is an, and which one of these is bn? So think that through for yourself and think about how that argument goes, right? Yeah. So the denominator is just a tiny bit larger. What happens to the overall value? Or the comparison of the overall values? Okay, good. So we keep going. All right, now S is a non-empty set bounded containing a sequence of rational numbers. Provide an example such that the least upper bound is not a rational number. Okay, yeah, so that's a pretty thank gosh, the dog is barking. Hang on. Get up there, boy. Huh. All right, we're back. Testing, testing. All right, so for a problem like this, we basically just really want to contrive like an upper bound, yeah? So I don't know. Let's say it's bounded, right? Let's just say the bottom is 0, and the idea here is that we would sort of want to like arbitrarily construct a. We sort of want to reverse engineer this, right? We're saying find find a set of S such that the least upper bound is not rational. But let's maybe like reverse engineer this, right? Let's maybe start with an upper bound that's least upper bound that's not rational and figure out what the set S has to look like. So choose your favorite irrational number, like square root of 2 or maybe pi, right? Um, pi is like 3.14159265358 etc., right? Um, yeah. So the idea here is if you just keep choosing points arbitrarily close to pi, getting closer and closer and closer but never touching it, then you've done exactly what the problem has asked you to do, right? So the only thing that's a little bit difficult is trying to choose every single one of these points to be rational, to be to be rational like the problem demands. And well, the easiest way to do that is to just look at this, right? Um, Gosh, I wish you could see my hand to cover up the screen, which would make this easier. But like, let me put it this way: the number 3 is a rational number, right? So far, so good. Um, okay, so this is a little bit distorted. Let's say that the first value is actually 3, right? This dot right here. Okay, so the value 3 is rational. I hope we can agree on that. Well, the value 3.1 is also rational. And the value 3.14 is also rational. See where I'm going with this? See where I'm going with this? Let's see if you can fill out the rest of the round. With just the minor caveat that sometimes when when a certain digit of pi is 0, which does happen, I believe, right? Like pi goes on for infinity. Um, and as far as anybody can guess, it seems to have a pretty uniform distribution of digits, at least from what I recall. Um, but yeah, the idea here is approximating pi to different values. Those approximations are less than pi itself, but well, more, but also happen to be rational. So play around with that and see if you can make that rigorous. Okay, finally, we're getting to a problem that actually asks us to do a little bit of calculation. So these are the Fibonacci numbers, right? Fibonacci, where an plus 1 is equal to an plus an minus 1. So what they're asking you to do is, well, bn, I think they say is equal to an plus 1 over an. Well, what do we got here? Let's just try to re-express some of this, shall we? So we already know an expression for an plus 1, yeah? Um, okay, what happens if we just go ahead and plug that in? So what are they asking us to do? They're trying to ask us to express bn in terms of bn minus 1. So maybe let's actually start by writing an expression for bn minus 1, which is just, um, let's put this down here. So if bn is equal to an plus 1 over an, then bn minus 1 has to be, well, you just bump each of those down. An over an minus 1. Yeah? So maybe just go ahead and plug in this value for an plus 1 and see if you can simplify and rewrite that a little bit, keeping in mind that we have this expression for an over an minus 1. And as a bit of a spoiler, you should get 1 plus something, where this something involves bn minus 1. You know, it's an expression involving bn minus 1. And also, 0 is less than or equal to something, and something is also less than or equal to 1. Right? And if the rest of the problem is asking you to show that bn is between 1 and 2, which is sort of equivalent to showing that something is between 0 and 1. And to show that something is between 0 and 1, I will maybe just let you play around with that idea a little bit, right? Just, uh, just, yeah, I wonder if I should, if I'm saying too much, if I give any hints on that regard. What are they trying to ask you to do? Yeah, show Bn is between 1 and 2. Yeah, it comes down to showing that that something term is between 0 and 1. And, at the risk of saying too much, right? Um, that something, again, is an expression involving Bn minus 1. So just look at what you can say about the value of Bn minus 1 given its definition, right? Can you say Bn minus 1 is equal to 1, greater than 1, less than 1? What can you say about it? And yeah, try to relate that to this something right here. Okay. So then the next part is saying that we want to show that Bn converges to some particular limit L. Or rather, they're telling us that it converges, and we're just being asked to find the value it converges to. So the sort of like quick and easy way of doing this is basically when the limit as n goes out to infinity of Bn, when this is equal to L, right? This is basically saying Bn is approximately equal to Bn minus 1, and that's approximately equal to L. So what this means is what our previous expression was, Bn is equal to 1 plus something, an expression of Bn minus 1. This is basically saying, all right, let's just do Bn, or let's just rewrite this as L is approximately equal to 1 plus something, which is an expression that used to depend on Bn minus 1, but now we're just approximating it as an expression of L. So we have L is about equal to 1 plus some other expression involving L. And the idea is you just gotta rewrite this expression. It's gonna turn into a quadratic equation after you replace this approximation with an equal sign. So it's gonna turn into a quadratic equation. Sorry, it's gonna turn into a quadratic polynomial in terms of L. So just solve for L. And spoilers, this should give you the very famous results of the golden ratio. The golden ratio. And just as one last reminder, the quadratic formula sometimes splits out a positive and a negative. Or rather, the quadratic formula can spit out two answers, right? And keep in mind that we showed earlier that Bn had to be between 1 and 2, right? 1 is less than or equal to Bn is less than or equal to 2, which means similarly that L has to be between these values. In fact, that was pretty much another exercise, right? That other exercise was basically, wait, which one was that? I think exercise 3, right? More or less the same idea. But if every single value of the sequence is sort of bounded by something, then that limit L also has to be bounded by that same something. All right, so that pretty much covers all the problems I was asked to do. I could quickly go over the rest that I think are pretty straightforward, maybe with one or two exceptions. But yeah, so the sequence, I think this is like, what is this, like 8? So if you're being asked to just integrate this thing, I don't even know what I can say about this problem really. Just remember how to integrate, right? So the limit as n goes to infinity. Just integrate this, and you should get, some expression evaluated from negative n to 0, and you just need to plug in those bounds and take the limit. Come on, boy. Huh. The dog was barking again. All right. Yeah, the next one is actually kind of a little more interesting. It's another invocation of the squeeze theorem, but we're considering sequence, what is this, like a to the n plus b to the n, so that 1 over n, the limit of this, right? And you're being asked whether it converges or diverges. And if it converges, find the value of the limit. So what we are told is that 0 is less than a is less than b. And just intuitively, the idea is that as n goes to infinity, because the base b is larger than the base a, it's sort of like b is going to end up dominating this behavior. That's sort of the idea here, right? Even though an exponential, a to the n is an exponential, and that grows fast, b to the n grows so much faster. That's the idea here. It dominates. So how would we prove that? Well, we're basically going to want to squeeze this with some really similar expressions. That's the idea. So what we know here is that, well, because a is less than b, right? This means that okay, so if this is the expression, right? How do I put it? A to the n plus b to the n. I actually don't know if this is increasing or decreasing now that I think about it. But the idea is, okay, so if this is the sequence, right? The idea is we want to bound it above with something else, and we want to bound it below with another thing. Sorry, I didn't draw that very well. And the idea is that we can show that this bottom sequence approaches some limit, and the top sequence approaches some limit, right? And that they each like sort of squeeze together that middle sequence. Well, then that middle sequence has got to approach that same limit. That's the idea, right? It's sort of like, there's one big fella over here pushing downwards, and there's this other big fella over here pushing upwards, right? And you're sort of stuck in the middle. You're sort of like being forced to go where they're going, essentially. So it comes down to, okay, so the middle one is basically the expression, our original expression. We just got to figure out a smart way to choose the big top and the bottom. And the way you might do that is basically, what's the easiest way to convey this? Well, just consider what happens if you just get rid of the an entirely, right? Just consider what happens if you get rid of the an entirely. Well, it's clear that just bn to the 1 over n has got to be less than a to the n plus b to the n times 1 over n, right? And similarly, because an or a was less than b, we know that a to the n is less than b to the n, which is another way of saying b to the n plus b to the n. Right? We can say that a to the n is less than b to the n, so this inequality holds. It should be a strict inequality, but it doesn't really matter. Now, to finish this sort of off, right? Basically, I'm wondering here, can you tell me anything about what these limits each approach? Well, this one's pretty obvious, right? This one's just b to the n to the 1 over n, this one's just b. But what's this limit? What's this limit? Well, this is another way of writing 2 times b to the n. And just think about what happens to this 2 as you apply the 1 over n exponential, right? And just think again about this picture that if there's a big person over here pushing downwards and a person over here pushing upwards, and these two, these two limits end up being the exact same, like they go towards the same place, right? Well, if you can just show that this has the same limit as this, then you're golden. And you'll be able to conclude that the middle one must also be the same. That's the idea here. So do that. Do that. Finish that argument. And make sure you understand it, all of that. All right, number 10 is 2 applications of L'Hopital's rule. For this one, all I have to say is, well, okay, they check the conditions to make sure at the start that it's in indeterminate form of 0 over 0. You just got to make sure to check that repeatedly. Does it actually follow all the requirements for L'Hopital at every step of the process? just check that really carefully. As for number 11, we're trying to use induction to show that ln of x to the n over x approaches 0. So this is a situation where induction, as you recall, is showing this is true for the base case. Sorry, is this as x approaches infinity? So the base case is when just you have ln of x over x, right? And I would recommend using L'Hopital's rule here to show that this approaches 0. So I'm going to this. No licking, dog. I'm babysitting my friend's dog, and this dog is really cute, but also kind of very eager to lick people. And I'm not the biggest fan of that. Okay, so where was I? So the base case is showing that the base case is showing that ln of x over x goes to 0, and the inductive step is showing that given that ln of x to the n minus 1 over x equals 0, you need to show the double arrow, the thick arrow means show or imply that ln of x to the n for x equal to 0. So this is a limit. So yeah, my recommendation in either case is for both showing the base case and showing the inductive step, is to use L'Hopital's rule. See if that gets you where you want to go. What's next? Okay. Yeah, so now we want to find an improper integral of the form a, b, fx. And you note that usually improper integrals are when a or b is infinity or negative infinity, but here they're asking you to choose just regular finite numbers. So this means that f of x, we need to choose an f of x that is a little bit nasty, that it has discontinuity or blows up, but doesn't blow up that bad to where its integral, area under the curve, still ends up being finite. So what I mean by that is, something like 1 over x squared blows up really, really, really fast at 0, right? 1 over x squared. And as it turns out that this area under the curve is infinite because it just gets too tall, too fast. But you have a similar situation with 1 over x, where you have a similar situation with 1 over x where the area under the curve still gets too fat, too tall, too fast, so the area grows too big and goes to infinity. But it's sort of a borderline case, right? It's just on the cusp. So my recommendation to you is to think about maybe a fractional power, or 1 over a fractional power, and see if that gives you where you want to go. See if that helps you out. And for this particular case, I guess I would choose a to be 0 and b to just be some like easy value like 1. Yeah. Try to see if you can find a situation where it goes up slowly enough. Sorry, that wasn't a good picture. If it goes up slowly enough, still goes to infinity, but slowly enough for this area from 0 to 1 to be finite. That's what you're being asked to do. And it's kind of counterintuitive, but it turns out that it's possible. Yeah. Of course, it doesn't have to be like centered or like it doesn't have to be oriented around 0 and 1, right? It could be totally anywhere else if you wanted to, right? You could have a situation where it looks something like this at like 5 for all you know. Yeah. But what's important here is the shape of the curve, and that's dictated by the power that x is raised to. I'm sure that there's other functions that look completely different that also achieve this effect, but I've sort of shared with you the easiest family of functions that I think will be the easiest to think about, the easiest to find. But anyways, on to our last question. I think we're being asked about cosine of 2 pi n. Now this is really weird to me because you're being asked to integrate this with respect to x, but you notice that there's not actually any value of x inside the argument here. So really this thing is just a constant. Like I'm wondering if this is a typo or what the heck. But yeah, this is just a constant. Now what this means is, well, what are you doing, boy? Yeah, this is just a constant, right? So the integration ought to be pretty simple. Anyways, maybe think through that and yeah, this question feels suspicious. It makes me feel like there might be a typo or something. I don't know. Yeah. Anyways, I think that's that. But yeah, if this is helpful, please like, subscribe, and if you have questions, comments, ask something. I'm super busy this week, but I try to make time because I like helping out. And engaging with this helps other students find what I do, and I hope to grow and reach more students and more classes over time. Well, take care and have a great evening.